So we're going to cover the enthalpy and reaction notes here. There's not a lot in terms of explanation, like definition-wise and stuff. It's just sort of like working through the problem. So we're going to work through the notes, and then whatever time we have left over, you guys will have to work on the homework that I handed you out. So, hey, focus. So, thermochemistry, the study of changes in heat within chemical reactions. So, energy transfer is linked hand in hand with chemical reactions. So, in chemistry, obviously, energy change and transfer and usage is super important. Okay, so the term enthalpy means refers to the change in heat for a reaction. Enthalpy technically just, I guess, would mean the heat of the reaction. The delta is change in, so it's designated by delta H. The delta, that's weird. The delta means change in. Okay. So when pressure remains constant, the heat absorbed or released during a chemical reaction is equal to the enthalpy change for the reaction. Then we have this equation here. The change in enthalpy can be calculated by taking the enthalpy of the products and subtracting the enthalpy of the reactants. In other words, what you end up with, subtract what you began with, that'll tell you the change. It's just like any other change in anything. Like you change in temperature, you take the final temp minus the initial. Okay, any kind of change in thing, you take the final minus the initial one. So this is just about the energy. Then we've got endothermic and exothermic, which we talked about before. Remember, endo, like enter, and exo, you can think of exit in terms of the energy either being absorbed or released from the reaction. So if the if your delta H, if your change in enthalpy is positive, it's an endothermic reaction because that means energy went in. It gained energy from the beginning to the end. If your change in enthalpy is positive. If your change in enthalpy is negative, that means it lost energy, which means it was an exothermic reaction. Everybody good with that? All right. Standard state of a substance. The standard state of a substance is the pure form, state of matter, of a substance at a standard pressure, 1 atmosphere. So we already did on the, we did on that homework, we were finding the certain changes at standard pressure, like the 1 atmosphere, like that's kind of what this was referring to. What state of matter will the substance be in at a pressure of 1 atmosphere? Now, obviously, here's the other thing obviously temperature affects the state of matter. So this is also sort of assuming a standard temperature as well. But they'll tell us that, and so we're looking at the 1 atmosphere thing. Standard enthalpy change is the enthalpy change measured when both the reactants and products of a reaction exist in their standard states, designated by delta H prime. Okay, so that's a little confusing, but it's basically just telling us that these are just regular, like standard, like that's how we're doing these things. Okay, like this is sort of just giving the green light to go ahead and do what we're going to be doing with the equations. All right, so the first thing is something called enthalpy diagrams. Enthalpy diagrams are a visual depiction of the relative enthalpy of the reactants and products in a reaction. All right, so you're given a reaction. Now, anybody remember what the stuff in the parentheses represents? Here? The state of matter, right? So like G is gas, S is solid, L is liquid. Okay. So we're told here, so this is an exothermic reaction because our delta H is negative. Okay. So all enthalpy diagrams, you're going to draw like sort of like an X and a Y axis, kind of like this. Okay. Your Y axis is going to be enthalpy. Designated by an H. And your x-axis is the reaction progress, or it's easier, I think it's easier just to think of it as kind of like time. Sometimes you'll see it designated, it'll say like literally like reaction progress, but in reality that's just time. Like as time goes along, the reaction goes on. Yeah.
This one over here, the endothermic reaction, the plus in front, do you have to put the plus?
No, I'm just doing it on these to show that, like to illustrate the difference on them. But no, you don't have to put that other plus on it. Okay, so here's how it works. If you notice, we've got no numbers or anything on our axis. And that's because we're just doing a graph that shows the relative enthalpy of reactants compared to products. So relative just means a comparison, right? So all we're concerned really with is which is bigger and which is smaller type of thing. If you have an exothermic reaction, that means, if you have exothermic, that means the reactants are bigger than the products. So in doing an enthalpy diagram, you always have, like, think about as time progresses. You start the reaction with the reactants and you end with the products, correct? So the reactants are going to be further to the left, the products are going to be further to the right. And then what you do is you look and you see which one, is it exothermic or endothermic? If it's exo, the reactants have more energy, more enthalpy than the products. So they will be higher up. So we are going to put the reactants up here, the whole side of the reactants. So I'm going to put this entire thing up like this. Okay. And I could make my x-axis a little longer here. I probably might have wanted that. Okay, so that's the entire reactant. I put them higher up because they have more energy than the products do. All right, now and I'm gonna, so see how I have these over to the left side, because we start with that. Now I'm gonna put the products, all of my products, I am going to put to the right. So kind of like this. And notice they're lower down because they have less energy than the reactants. Now, the only thing you do, the only extra thing you do, or well, a couple things I guess here, is the arrow. You put the arrow in, and you always take the arrow from the reactants to the products, just like it is in the equation. So we just draw an arrow from this line to this line like that. It just shows the direction of the reaction. And then next to, usually next to this line, or you can kind of put up the side a little bit, but you put the delta H equals, you put what the delta H is.
With the label as well?
Yep. So like that.
So if it was endothermic, it would just be that the reactants are lower and the products are higher?
Yep.
Okay.
Yeah, so let's go ahead and do this one. So it's the same kind of setup. We're going to do, this is enthalpy. And this is going to be time. Okay, and so this is exactly like what Cora was asking here. The endothermic means that our products have more energy than our reactants. So that means the reactants are going to be lower and the products higher, but we do it the same way here. The reactants are going to be on the left side. So reactants over here, but they're lower down. So I'm going to do C solid plus H2O gas. Okay, and then my products are going to be higher up. My arrow goes from my reactants to my products. Okay, like that. And then all I need is my delta H. Like that.
Oh, you have to put like the S and G after.
Yeah, I want you to put, because the state of matter matters. In other words, like, so for example, if you think about water, water as a gas contains more energy than water as a liquid does. So that would actually change the amount of energy. So yes, you should put the states of matter in. All right. Any other questions on the diagram parts? All right. So go ahead and do an enthalpy diagram for the bottom one here. Okay. All right. So let's see. So hopefully it looks something like this. You got your enthalpy and your time, and then because it's negative, that means it's an exothermic reaction, which means reactants are higher than products. And then you've got your arrow going from reactants to products and your delta H labeled there. Yeah.
I had everything right except for I put.
And we'll do the calculating enthalpy changes. All right. So the delta H prime for a reaction, sometimes it'll be shown as delta H prime sub Rxn, which means reaction, same thing, is the enthalpy change for one, quote, occurrence of that reaction. So like, basically, if you think of it, if you think of it like a recipe, like the delta H is for running this through once, like with these numbers and stuff in it. Okay, so in other words, for 1 mole of the C3H8, 5 moles of the O2, you'll produce 3 moles of CO and 4 moles of H2O. And for that specific amount of that reaction, it would release 2,043 kilojoules. Okay. So you can create ratios between the moles of reactants and products and the energy gained or lost, the change in energy. Okay, so for example, what would the enthalpy change be if 12 moles of O2 gas were reacted according to the above equation up here? So here's what we do. We're going to use our dimensional analysis that we've been doing for a whole semester now, basically. Start with the 12 moles of O2. Like this. 12 moles of O2 gas. And we are going to create a conversion using the coefficients up here, because these represent number of moles, and the energy change. So what this equation tells us is, so we've got moles of O2 gas here, right? So moles of O2 gas goes on the bottom, so we can cancel it. So it's just the same thing in terms of where the labels go that we've done before. So moles of O2 gas goes here, and we're going to turn it into energy. So the kilojoules is our label on our energy. So that goes on top. Okay, here's how we do it. The number that goes in front of the moles comes from the coefficients in front of that substance. So you find the O2 gas. O2 gas is here. What's the coefficient? So that goes down here in front of the moles of O2 gas. So this is the so that's from the coefficient. Okay. Then in front of the kilojoules, so we know that this equation, there's 5 moles of oxygen. If 5 moles of oxygen gas are involved, it will produce an energy loss of negative 2,043 kilojoules. So in front of the kilojoules, negative 2043. This is the, whatever your delta H prime is, that number goes with the kilojoules. So I got that from over here. So they have to give you this, the balance equation and the delta H prime. Okay, then all we do is we do the math. Moles of O2 cancels with kilojoules. This comes out to be like something like negative 4,903.2. And then if we round it significant figures, you got 2 here, so it'd be negative 4,900 kilojoules is our answer. Make sense? Okay. Let's do the second example. How much heat is transferred when 19.22 grams of methane burns in excess oxygen according to the following equation? So same type of deal. We're just taking the 19.22 grams of methane. And if you don't know what methane is, look here, and it's going to be the only one you don't know. This is oxygen, it's carbon dioxide, that's water. So it has to be this. So we do 19.22 grams of the C8H18 gas. Okay. So it's basically the same thing we were doing before, except they start us in grams. So what's the first thing we have to do? Good. We go grams to moles. So this is the same gram to mole conversion we've been doing all year. So it's 1 in front of the mole. This is the molar mass. So it'd be 8 times 16 plus 18 would be, what's that, 114? Okay, now that we're in moles, now we want how much heat, so that's energy, so we're trying to turn this into energy. So moles of C8H18 goes in the bottom. We're turning it into kilojoules. Okay. What number is going to go in front of the moles of C8H18?
2.
Good, from the coefficient here. Okay. And in front of the kilojoules, negative 2,803 from our delta H. And then we can just do the math. And 4 significant figures. So this comes out to be negative 236.3 kilojoules. So one more step in this, but it's just that step we've done, like I said, hundreds of times now, the grams to moles conversion. All right. So, all right, save the best for last. By best, I mean most complicated. So we've got how much heat is transferred when 147 grams of NO2 gas is dissolved in 100 grams of water. Also create an enthalpy diagram for the reaction. So let's do the diagram first. So we're going to do, you're going to need to leave some room on the bottom here to do the problem. So we've got enthalpy. And we've got time. Okay. So are our reactants going to be high or low? Good, because it's what type of reaction? Endo or exothermic? Exo, good. Negative tells us exothermic, so our reactants are going to be higher up. Okay, and then our products are going to be a little lower down. The AQ, by the way, means aqueous. That's like a solid dissolved in water. Okay, our arrow goes from reactants to products, right? Like this. And then we just put our delta H kind of off to the side. Bless you. All right. So I'm assuming diagram makes sense. Everybody's good with that. All right. Now we have a little problem here where they give us 147 grams of NO2 gas, this, 100 grams of water, this. They give us 2 reactants. So this actually goes back to some of the stuff we did before. We have to figure out which one is the limiting reactant. Okay, now we're not going to have to run a BCA chart for this, but we do have to figure out the limiting reactant. So, anybody remember the first thing we want to do with these numbers? Good. Turn grams to moles, right? So we're going to start 147 grams of NO2, and we're going to turn grams of NO2 into moles of NO2. And that is, NO2 is 1 times nitrogen, 2 times oxygen, so that's 46. Okay. Okay, so this comes out to be 3 significant figures, so 3.20 moles of the NO2. We're going to do the same thing with the water, 100 grams of water. I'm going to turn grams to moles. Water is 18 grams for 1 mole. And this comes out to be 3 significant figures again, 5.56. All right. So far, so good. All right, limiting reactant. Now, there's one other step we have to do before we can figure out which one the limiting reactant is. Anybody remember what that is? Good. Divide by the coefficients. So what's in front of NO2? Okay, so we're going to divide that one by 3. What's in front of the H2O? Nothing, so a 1. Okay, so this comes out to be 1.07 of the that one, and then this comes out, this stays 5.56. So which one's our limiting reactant? Okay, so, and you don't have to write this down. I'm just doing it to kind of show on the notes here. So the limiting reactant is the NO2, right? So, anybody know why we had to find the limiting reactant? Because once the limiting reactant is used up, then what happens? Okay. Yeah. Yeah. Yeah, reaction stops. So just like everything else in terms of like when we're figuring out like how much product is made, all that kind of stuff, it also determines like how much energy the reaction either gives off or absorbs. Okay. So now here's the part where I don't necessarily say it's like tricky, but like you just kind of have to sort of pay attention and understand what's happening here. So when we had, let me see if I can zoom out a little bit here. Okay, up here, when we had moles of our substance, right? We converted. So again, we want to know how much heat is transferred. So we're looking for energy. When we had moles of our substance, we converted from moles to energy, kilojoules, using the dividing by the coefficient, and then on the top we would have the delta H, right? So if we look down here on the limiting reactant one, we have already divided by what? The coefficient. So we've already done this part of it. So the only thing we have left to do to figure out the amount of energy is multiply by the delta H. That makes sense?
Why wouldn't we divide?
Because you're turning, so here, hold on. Okay, so let's say, get this in here so you can see it. So let's say we had 3.20 moles of NO2, right? And I said that we wanted to know how much energy that's going to transfer, how much heat that's going to produce, whatever. So we would do this, right? Moles of NO2 on here. So we go moles of NO2, we turn it into kilojoules, right? So in front of the moles of NO2, we do the coefficient, so it's a 3. In front of the kilojoules, the delta H, so it's negative 138, like this. So to figure this out, we do this times this divided by that, right? Okay, so we've already in a way, we've already divided, so we've already done this part of it here. That's this. We've already done the dividing by the moles to cancel that. All that's left is this part, which is multiplied.
Okay.
Does that help? Okay. So we're just going to multiply times the delta H okay, and this comes out to be significant figures are 3, so rounded it comes out to be negative 148 kilojoules. Okay. Now, if this part here, like if this is a little confusing, what you can do, you still have to divide by the coefficient to find the limiting reactant, but after you find the limiting reactant, if like this still is like a little confusing to you, you can then just take the moles and then do this, and you'll get the same answer. Okay, like, but remember, don't take this number, take this number and convert. Okay. All right. Put this on the video too. On the homework, the enthalpy of reactions and enthalpy diagram number 1. These problems, you're going to be doing the diagram, doing the enthalpy diagrams, and then you're going to be calculating the energy. But there are no problems on here on this first sheet that are like the third one from the notes like this. There's none that you're going to have to do the limiting reactant stuff on this homework sheet. Okay, they'll all be like kind of like the first couple examples. Okay.